Welcome back to Introduction to Higher Mathematics. In our last lecture, we introduced modular arithmetic, which centers around congruence. Two integers a and b are congruent modulo some number m if a minus b is a multiple of m. We learned about fundamental properties of congruence mod m, seeing how addition, multiplication, and exponentiation work, and how congruence mod m partitions the integers into distinct congruence classes. We investigated linear congruences of the form ax is congruent to b mod m, and saw that such congruences can have solutions from one or more congruence classes, or perhaps no solutions at all. We defined the multiplicative inverse of a mod m as the number by which a is multiplied so that the product is congruent to 1 mod m. We explored two applications of modular arithmetic: divisibility rules, which let us devise rules to easily test divisibility by certain numbers, and RSA public key cryptography, a relatively simple cryptography system that's secure because of our difficulty to factor rather large numbers. Finally, we distilled our idea of modular arithmetic to create the residue system ZM, in which we add and multiply congruence classes directly, treating them as abstract objects of their own. When we constructed ZM from the integers, we took something infinite and turned it into something finite. We like things that are finite. They're relatively easy to visualize and manage. The infinite, on the other hand, tends to both mystify and terrify us as human beings. So in this lecture, our goal is to tackle the infinite and get an idea of how it works. To begin our exploration of infinity, we need to more thoroughly visit a concept we briefly touched on a few lectures ago, the concept of cardinality. The cardinality of a set is what we call the number of elements in the set. In other words, the, quote, size of that set. So suppose I have a set A, which is the set 2, 4, 6, 8, 10. Then we can count the elements of A, 1, 2, 3, 4, 5. So the cardinality of A is 5. We write the cardinality of a set with absolute value bars, since the absolute value of a number basically also measures the size of that number. The concept of cardinality is as ancient as mankind's quest to understand numbers. In fact, the comprehension of numbers as an abstract concept rather than a concrete thing is a truly remarkable milestone in the history of our species. For instance, we often see things that come in pairs. Our bodies each have 2 eyes, 2 ears, 2 hands, 2 feet, and so on. But we don't usually see a numeral 2 anywhere in nature. Nonetheless, anything that comes in pairs is unified by a sort of two-ness. As Bertrand Russell once said in his book, Introduction to Mathematical Philosophy, it must have required many ages to discover that a brace of pheasants and a couple of days were both instances of the number 2. Even when humans did begin to understand the concept of abstract numbers, our vocabulary was very limited. Many primitive cultures had only 3 words for numbers, which corresponded with the ideas of 1, 2, and many. Even today, the remnants of this limited number system can be seen in Semitic languages like Hebrew and Arabic, in which nouns can be singular, dual, or plural in number. How then might an ancient shepherd letting his sheep out to graze in the morning make sure that they have all returned in the evening? Well, suppose this shepherd had a small patch of stones, and let's say he had 5 sheep. Though of course he wouldn't know that there were 5, as such a concept would be foreign to him. For every sheep that leaves, the shepherd might lay out a stone. So once all the sheep are out grazing, unbeknownst to the shepherd, but knownst to us, the shepherd would have 5 stones laid out. Now come evening, every time a sheep comes in from the fields, the shepherd would take one of those stones and put it back into his pouch. If by nightfall there were still stones that hadn't been put away yet, the shepherd would know something was wrong. Perhaps that sheep had become a wolf's lunch. Of course, if a sheep came in when there were no stones left, then that would be a different kind of problem entirely. Anyway, by pairing each stone up with exactly 1 sheep, the shepherd can keep track of all of them without even needing to count them explicitly. This might look familiar from when we talked about functions a few lectures ago. What the shepherd has done in this case is he has established a bijection between stones and sheep. Remember that we said that when we've got a bijection between 2 sets, we've shown that those 2 sets have the same cardinality. We still use this same idea today when we count objects, except that instead of using stones, we use words or symbols that represent those words. So we've seen what happens when two sets have the same cardinality. But what if they don't? Well, it turns out that two sets have the same cardinality if and only if there exists a bijection between them. So if two sets do not have the same cardinality, it is impossible to establish a bijection between them. Again, consider the set A equals 2, 4, 6, 8, 10, and now the set B, 1, 3, 5, 7, 9, 11. What happens if we try to establish a function f from A to B? Perhaps we let f of 2 be 1, f of 4 be 3, f of 6 be 5, and f of 8 be 7, and then finally f of 10 be 9. Notice that the element 11 never gets mapped to. No matter how hard we try, there will always be an element of B that is left out, not mapped to by any element of A. So, since the cardinality of our domain is less than the cardinality of our codomain, our function can never be surjective. On the other hand, what happens if we try to establish a bijection the opposite way? Say, a function g from B to A. Perhaps g of 1 is 2, g of 3 is 4, g of 5 is 6, g of 7 is 8, and g of 9 is 10. But for g to be a function, 11 has to map to something as well. So what has to happen is that 11 has to map to an element of A that's already been mapped to by some other element of A. Again, no matter how hard we try, there will always be an element of A that is mapped to by two elements of B. So since the cardinality of our codomain is in this case larger than the cardinality of our codomain, our function can never be injective. There's actually a colloquial name for this second result. It's often called the pigeonhole principle, named for the little spaces you might see in a pigeon loft. Informally, the pigeonhole principle can be stated like this. If there are more pigeons than there are holes to put them in, then there must be at least one hole that contains more than one pigeon. Basically, our domain is the pigeons, our codomain is the holes, and the function places pigeons into holes. Thus, if there are more pigeons than holes, then there is no injection from pigeons to holes. On the other hand, if we can find an injection from A to B, as well as an injection from B to A, then there must be a bijective function between A and B as well. This result is called the Cantor-Bernstein-Schroeder theorem, named after Georg Cantor, whom we met in Lecture 5 as the inventor of set theory, as well as German mathematicians Felix Bernstein and Ernst Schröder. Cardinality is a pretty easy thing to deal with for finite sets. However, once we start dealing with infinity, things get a bit more interesting and bizarre. Suppose we consider our set A from earlier, and this time consider a set C equals 2, 6, 10. We can see that C is a subset of A. Not only that, it's a proper subset of A. What's more, the cardinality of C is less than that of A. For finite sets, these two statements go hand in hand. A proper subset of a finite set will always have a strictly smaller cardinality than the original set. This seems intuitive and almost obvious. But in the 17th century, Italian physicist and mathematician Galileo Galilei discovered a curious paradox that occurred when trying to apply this idea to infinite sets. He published his findings in his final scientific work, Two New Sciences, in 1638. It's easy to see that the perfect squares, 1, 4, 9, 16, 25, and so on, are a proper subset of all the natural numbers. So this suggests that there are fewer perfect squares than there are natural numbers. But Galileo noticed that if those perfect squares were placed right under their positive square roots, then every natural number matched up exactly with some perfect square, with no numbers left out in either list. So this seemed to suggest that there were exactly as many perfect squares as there were natural numbers. This paradox baffled him, and he left it unresolved, concluding that the ideas of equal, lesser, or greater cardinality simply didn't make sense in the context of infinite sets. It wasn't until over 200 years later that this paradox was finally resolved by none other than Cantor. Remember that the ideas behind set theory had already been known since ancient times. However, at that time, only finite sets were considered, and the concept of infinity was considered a topic of philosophical rather than mathematical study. Cantor's work on set theory changed this idea forever. It was in fact Cantor who established that if one could find a bijection between two sets, then the sets had the same cardinality. This is often referred to as finding a one-to-one correspondence, though be careful. This is different from saying that a function is one-to-one, which only means injective, not bijective. Cantor gave the cardinality of the natural numbers its own name. He called it Aleph Null. Aleph is the first letter of the Hebrew alphabet. From there, he defined a countable set as a set with the same cardinality as some subset of the natural numbers. Remember that when we count something, say 5 sheep, we're pairing each one with a natural number, starting at 1 and incrementing by 1 each time. So the function that does this is a bijection between the set of sheep and the set 1, 2, 3, 4, 5. Since that second set is a subset of the natural numbers, we say that the set of sheep is countable. It should come as no surprise that any finite set is therefore countable. But, for example, the perfect squares are a countable set as well, because they have the same cardinality as the natural numbers. And n is certainly a subset of itself, albeit not a proper subset. We call such a set countably infinite. If a set is countably infinite, its cardinality is Aleph Null. We can still count such a set, even though we would be stuck counting forever. We can take this one step further, though. Remember when we said that although a set is not ordered, we could make it ordered by indexing it with the natural numbers? Well, if we can index a set with the natural numbers and ensure that no element of the set will be left out, then we can conclude that it must be countable. So, for example, the even natural numbers are countable. All we have to do is list them. So we could say that the first even natural number is 2, the second even natural number is 4, the third is 6, the fourth is 8, and so on. In particular, we can actually explicitly state our bijection. First of all, our injection we're using from the natural numbers to the even natural numbers is f of n equals 2 times n. Second of all, its inverse, n over 2, is an injection from the even natural numbers to the natural numbers. Thus, according to the Cantor-Bernstein-Schroeder theorem, f of n is a bijection, and so we've shown that the even natural numbers are in fact countable. Let's look at some other infinite sets and see if they're countable. We'll start with the integers. Are the integers countable? Well, let's see if we can put them in some order such that we won't miss any of them. So we might start off by listing the natural numbers first, 1, 2, 3, 4, and so on. Then when we're done with those, we can list 0 and the negative numbers. What's wrong with this logic? We'll never be done. There's no such thing as being done listing the natural numbers, because there's an infinite number of them. So we need a more clever approach. Perhaps we could list 0 first, then 1, then negative 1, then 2, then negative 2, and so on, fanning out from the middle. So the even index terms take care of the natural numbers, and the odd index terms take care of the 0 and the negative counterparts of the natural numbers. We could write the bijection that we're using as well, though in this case, it would have to be a piecewise defined function. Look at just the even index terms. Each of those is half the natural number above them. So if n is even, f of n is n over 2. Now look at just the odd index terms. Notice that both sequences of terms are just arithmetic sequences. So the function should be linear. We can just solve for the slope, negative 1/2, and then plug in one of the points. So if n is odd, f of n is 1 minus n over 2. There we go. There's our injection between the natural numbers and the integers. We can find its inverse too. If an integer z is greater than 0, then f inverse of z is 2z. And if z is less than or equal to 0, then f inverse of z is 1 minus 2z. Feel free to plug some values into f and f inverse to see how they work. F of n tells you what the nth integer in the list will be, and f inverse of z tells you the index of the integer z. Thus, f is our bijection, and we conclude that the integers are in fact countable. So that takes care of the integers. But what about the rational numbers? It at least seems plausible that the even numbers and the integers have the same cardinality as the natural numbers. But in the case of the rational numbers, there are an infinite number of fractions just between 0 and 1. Not only that, but listing them seems near impossible. Where would we even begin? So it might seem at first glance that the cardinality of the rational numbers has to be larger somehow than the cardinality of the natural numbers. Even so, let's explore this problem a bit. Maybe there's a surprise in store for us. Let's consider just the positive rational numbers. Remember that every rational number can be represented as a ratio of two integers, hence the name. So the positive rational numbers could be represented as a ratio of two natural numbers. Since we need two natural numbers to define a positive rational number, we could perhaps make a table of the rational numbers, like this. The row at the top represents the numerator, and the column represents the denominator. It's not a list, but we're starting to get somewhere, because every positive rational number has to be somewhere in this list. If you give me a rational number, m over n, I can tell you exactly where it is, the mth column and the nth row. With that in mind, though, how can we possibly list every number in the table? We can't list them row by row, because we would be writing the first row forever before we even got to the second. Similarly, we can't list them column by column. But look at this. What if we start at 1 over 1, which is 1, then move 1 over to the right, we'll be at 2 over 1, which is 2. Now move diagonally down to the left, 1/2. Now down, 1/3. Now diagonally again up and to the right, 2 over 2, which is 1. We've already listed this one, so we'll leave it out. Up and to the right again, 3 over 1, which is 3. Now right again, 4 over 1, which is 4. And now you start to see the pattern that's forming. We're taking a snake-like path, moving diagonally until we reach the edge, shifting to the next level, and moving diagonally again in the opposite direction. If we move like this, we're guaranteed to hit every single row. See if you can prove this by determining which level a particular rational number m over n will be on, in terms of m and n. So amazingly, we've actually managed to come up with a way to actually list all of the positive rational numbers. Then to extend this to all the rational numbers, positive, negative, and 0, we can use the same strategy as the integers, listing 0 first, then swapping between positive and negative rationals in the order we just discovered. And there you have it. We've managed to find a way to list every single rational number. Thus, the rational numbers, believe it or not, are actually countable. So now we've shown that the natural numbers, the integers, and even the rational numbers are all countable. Well, this leaves us no choice but to try to go one step further and look at the real numbers. Given how surprising the last result is, perhaps it might be the case that even the real numbers are countable too in some way, wouldn't you think? The answer to this question was proven by Cantor, and is one of the things for which he is best known. For right now, we're just going to consider the real numbers between 0 and 1 inclusive. If the real numbers are countable, surely a proper subset of it will be countable as well. Given any real number between 0 and 1, whether rational or irrational, we can always represent it by some infinite sequence of digits after the decimal point. For instance, the number 1/2, which you know is equal to 0.5, can be represented as 0.50000 and so on, with the zeros repeating forever. Any terminating decimal can be represented like this. On the other hand, an irrational number such as 1 over pi would have a sequence of digits that goes on forever after the decimal point, yet never repeats. The conditional works the other way too. Any sequence of digits we can come up with after the decimal point corresponds to some real number. So, let's suppose that the real numbers between 0 and 1 were in fact countable. This means that we would be able to index them with the natural numbers, and so we could list them out. So let's do that. Perhaps our list might look something like this. The idea is if the real numbers between 0 and 1 are countable, then this list should contain all of those numbers at some point in the list. Now, to make things interesting, I'm going to introduce a little rule to create a new number b out of the ones in the list. We'll say that b starts off as 0 point something to make sure it's between 0 and 1. And then the rule goes like this. For the nth number in the list, look at the nth digit. If the nth digit of that number is anything but 5, we'll say that the nth digit of b is 5. If the nth digit of that number is 5, though, we'll say that the nth digit of b is 4. So let's see what b begins to look like. So the first digit of our first number is 5. So the first digit of b we change to 4. The second digit of our second number is 0, which isn't 5. So the second digit of b is 5. The third digit of our third number is 8. So the third digit of b is 5. The fourth digit of our fourth number is 5. So the fourth digit of b is 4. The fifth digit of our fifth number is 1. So the fifth number of b is 5. And we keep doing this all the way down the line. For any natural number n, we know what the nth digit of b is. Now, here's a question. Where is b in our list? Remember, we've said that our list contains all the real numbers between 0 and 1. So the real number b should be somewhere on the list. Is it the first number? Well, no, it can't be. The first digits of each number are different. Is it the second number? No, again, the second digits are different. What about the third number? Nope, the third digits are different. It can't be the fourth number since the fourth digits are different. It can't be the fifth number since the fifth digits are different. Uh-oh, we've got a problem here. No matter what n we pick, b can't be the nth number, because it has to be different in the nth digit. So it would seem that b isn't in our list. But what does that mean? Well, since b is a real number that isn't in our list, it means that our list doesn't contain all the real numbers between 0 and 1. So the set of real numbers between 0 and 1 has a cardinality that is greater than that of the set of natural numbers. There is no bijection between the two sets. In other words, we've managed to show that the real numbers are actually uncountable. This argument is called Cantor's diagonal method, since it was Cantor who discovered it in his Inquiries into Infinity. The consequences of Cantor's findings were huge. What Cantor had done was he had proven that there were in fact different sizes of infinity. The cardinality of the natural numbers was infinite, but the cardinality of the real numbers was an even larger infinity, which we often call the cardinality of the continuum, represented with the lowercase fractor letter c, like the old German style of calligraphy. This idea, like many revolutionary ideas, wasn't exactly received warmly. Cantor's contemporaries vehemently rejected his ideas, most notably German mathematician Leopold Kronecker, who was quoted as having said, "God made the natural numbers. All else is the work of man." Kronecker was what was called a finitist, a mathematician who didn't believe that these sort of infinities existed. He attacked Cantor's ideas fiercely and quite personally, and many other mathematicians joined him. It's thought that the hostility Cantor encountered from his contemporaries may have been a contributing factor to the depression from which he suffered until he died in 1884. Many years afterward, though, mathematicians began to realize just how essential Cantor's contribution to the history of mathematics was, and ever since then, his findings have become part of standard mathematics curricula everywhere. In particular, David Hilbert recognized that Cantor's findings had forever changed mathematics. As he said, "No one shall expel us from the paradise that Cantor has created." In fact, Hilbert himself is known for his observations on infinity and its strange, even counterintuitive properties. He illustrated some of these observations in what is now known as Hilbert's paradox of the Grand Hotel. Imagine there's a hotel that has a countably infinite number of rooms, and that on some particular night all of the rooms are full. Now suppose a new guest comes to check into the hotel. If the hotel had a finite number of rooms, the guest would have to be turned away. But the fact that there's a countably infinite number of rooms allows for a bizarre yet simple solution. The hotel simply asks the guest in room number 1 to move to room number 2. Then the guest in room number 2 moves to room number 3. The guest in room number 3 moves to room number 4, and so on, freeing up the first room for the new guest. But wait, you say, won't the guest at the end have nowhere to go? Again, if there were a finite number of rooms, this would be the case. But Hilbert's hotel doesn't have that problem. If you tell me what room a particular guest is staying in, I can without hesitation tell you exactly what room that guest has moved to. There is no guest at the end. In a way, what this says in a very non-strict sense is that despite what many children over the years have said in their attempts to outdo each other, infinity plus 1 is in fact equal to infinity. Getting back to the hotel, though, we can take our problem one step further. Suppose this time that not 1, not 2, not even 100 or 1,000, but a countably infinite number of guests arrived at the hotel. If we were being asked to accommodate a finite number of guests, we could have just repeated the process from before but had each guest move down a few more rooms. But with an infinite number of new guests, we can't exactly move each person down an infinite number of rooms, can we? Well, there's still a solution. We could move the guest in room number 1 to room number 2. Then the guest in room number 2 to room number 4. Then the guest in room number 3 to room number 6, and so on, moving each guest to twice his or her current room number. Now only the even-numbered rooms are occupied, and the odd-numbered rooms are vacant. And since the set of odd numbers is the same size as the set of natural numbers, we can put everybody into the odd-numbered rooms. Problem solved. Again, you may wonder whether somebody got left out, but if you tell me the room number anybody was in, I can tell you what room they were moved to. What's more, if you were to give each of the people in line a number, I could tell them exactly which room they're assigned to. Again, the uniqueness of how infinity works is what provides our solution. This is why we can't do math with infinity quite the same way we can with other numbers. It follows a completely different set of rules. Well, that should be it for this lecture. Next time, we'll begin going a bit deeper into the real numbers and see why they're often the ideal number system with which to do mathematics. See you next time.